The weather is to invent it. And you know, there's a number of us at the University of Washington who are working on weather prediction technology. So I think that gives us a little bit of insight into what's going to be happening. So some of the questions that I'm going to be answering today is, how will the technology of Northwest weather prediction change? Will the very nature of the forecast change? How will the delivery of forecasts, how we present it, how will that evolve? And will users make use of forecasts in a new way? These are some of the questions, and then I'll be open to other questions after. If you want to talk about things, I even can talk about global warming if you want. That's very popular around here. Okay, we won't get into that right now, or we won't get in trouble. As many of you know, the key technology, the technology that really is the foundation for all weather forecasts, is numerical weather prediction. And so I want to give you a little bit of a background on numerical weather prediction. The basic idea is that if we can determine the current state of the atmosphere, and we have a big name for this, we call this the initialization. We can get all the observations together and describe what's happening right now. You can predict the future of the atmosphere using equations that describe the atmospheric physics. And we solve these equations generally on a three-dimensional grid. You can think of the whole atmosphere in terms of a three-dimensional grid. And here's some of the equations. We call this the primitive equations, but they're not really primitive. In fact, these are the core equations that we use. The ones that basically in Newton's second law, F equals ma, conservation of mass, conservation of energy, conservation of moisture. These are the core equations. In fact, current numerical models are the number of lines of code extend from the hundreds of thousands to millions. Okay, the numerical models today are one of the most complex constructs of our species. They're amazingly complex animals. Now, numerical weather prediction is done on computers. It started, the first numerical weather prediction was in 1950, and that's when they first had digital computers available. Numerical weather prediction is limited by the available computer resources. And certainly as computer speed increases, the number of grid points can be increased. If we have more grid points, they can be closer and closer together, which means we have more and more resolution. We can describe finer and finer scale features. And in fact, here's a net of computers used by the National Weather Service. The operational numerical weather service, the operational computers used by the Weather Service has about almost 5,000 processors. This is what they're using today. Now, to give you, we've had an amazing improvement over the last 50 years in numerical weather prediction. Back in the 50s, when it started, the spacing of that grid that we solved the equations on was about 700 kilometers. Today, the National Weather Service is running down to 4 kilometers. In fact, they're running down experimentally to 1.3. The University of Washington, we're running operationally down to 1.3 kilometers. So imagine 700 kilometers in the 50s to 1.3 kilometers today. Now, faster computers not only let you have finer grid spacing, but they allow you to include more of the physics to better represent the physical processes in the models, like clouds and radiation, things like that. Another big change in numerical weather prediction is that we have so much more data available to us to have a much better starting point, a much better initialization. We'll be getting back to that over and over again, but we have vastly improved data resources now. So putting all this together, forecasts have improved. And in fact, this is an old slide I have. This is from the National Weather Service. This shows you the improvement of forecasts by the National Weather Service model, global model, at 500 hectopascals, 500 millibars. This is about halfway up in the mass of the atmosphere, about 18,000 feet. And basically, I'm not going to tell you what an S1 score is, but basically we're going from 1950 all the way to 2000. And this shows you the error from the 36-hour forecast and the 72. And you notice the steady progression, the improvement of forecasts. And we have come a long way. Before 1990, we got virtually all the major cyclones that struck the West Coast, we got wrong. After 1990, we got almost all of them right. Like the Columbus Day storm in 1962. That forecast was pretty bad, my friends. It was a terrible forecast. But 1993, the Inauguration Day storm, we did very well. The December 12th, 95 storm, we did very well. The Hanukkah Eve storm in 2006. So we've gone from getting virtually all the major storms hitting the West Coast wrong to virtually all of them right. And that's a tremendous jump due to the improvements in terms of numerical weather prediction. So making fun of meteorologists is not a good idea. A slide that I think is the one really just so eloquently shows how far we've come is this one. This shows you the improvements of the gold standard numerical weather prediction in the world. And that is from the European Center for Medium Range Forecasting. It's an embarrassment as an American to admit that the #1 forecasting entity in the world, global forecast, is not American. It's the European Center, centered in Reading, England. Anyway, this shows you the change from 1981 to 2010. Basically, this shows you basically skill. Higher is better for day 3, 4, 5, 7, and 10. And the top line in each of these color things, the top is the northern hemisphere, and the bottom is the southern hemisphere. Now, two things strike you. First, it's going up, right? And 100% is perfect, would be a perfect forecast. And the skill has increased. But one thing I want you to notice, the difference between the northern hemisphere and the southern hemisphere skill has dropped to almost 0. Why is that? Why is the northern hemisphere? Now, in the past, the northern hemisphere had better forecast skill because there were a lot more observations there, right? A lot more land area, a lot of countries, China, Europe, US, that's where a lot of observations were. And there's more land area. Why is the forecast skill almost identical now? What do you think?
Easier to model?
What?
Easier to model?
Remote satellites.
What? The satellites. Right now, satellites are the key observational asset. 95 to 98% of the raw number of observations that go into numerical weather prediction now are from satellites. We have as much satellite observations in the southern hemisphere and the northern hemisphere. Some people talk about, sometimes TV weather people, not only the TV weather people in this room, but sometimes TV weather people talk about the data void over the Pacific. And that makes it difficult to forecast. But that's not true anymore. That data void doesn't exist because now we have a huge amount of satellite observations over the ocean. So, Pacific data voids, the one thing you want to leave here, one big change, the Pacific data void no longer exists. Just to prove this to you, here's the West Coast over there, all right? Is this working here? Maybe not. There we go. So West Coast is over here.
Yeah.
One thing we can do from the satellites is we can track the clouds. These are called cloud track winds. We can track the clouds and see where they're moving. And so, we can do that over the oceans. And so we can see how the clouds are moving everywhere. And we can see how high the clouds are, either from our satellites too, or infrared satellites. We can not only do this, we can track moisture in the atmosphere as well. It's moisture track winds. So right now we are getting tens of thousands of these kind of wind observations globally from our satellites over the oceans. So this whole idea about data void is not true. So we're getting massive observations, and this has contributed hugely to numerical weather predictions. But it's better than that. You ever watch Star Trek? You can like Spock if you're an old guy like me, or Data if you watch Next Generation. I mean, when they'd go around a new planet, they'd scan the planet, right? They get all this information about the meteorology. Well, we can do the same thing today, better than Star Trek. We can look down on the satellites in various wavelengths, and we can get soundings, how temperature and humidity changes with light everywhere on the planet. We can do that. But it's even better than that. We have a new series of satellites that get these are GPS satellites. It's a cosmic constellation of satellites. And what these satellites do is, everybody knows about GPS, right? There's GPS satellites up there, and you have GPS in your car, you're receiving signals from those satellites. Well, if you have another satellite that's receiving the signal, it can measure how long it takes the GPS satellite signal to go through the Earth's atmosphere. And so as the receiving satellite moves down like this, the signal from the GPS satellite has to scan through the Earth's atmosphere, and you can actually get temperatures and humidities with height from these satellites by receiving the GPS signal. And you can get not one, but hundreds or thousands of soundings around the planet each day from receiving the GPS signals.